Hello dear students, in chapter 6 entitled Volumetric Titration, we're going to learn the following objectives. Define volumetric titration, give the characteristics of a titration reaction, identify complete redox reactions, recognize the principle of a volumetric titration in a redox reaction, draw the setup of titration and write the procedure, define equivalence in the titration of a redox reaction, determine the equivalence, and determine the concentration of the solution being titrated. Please, while watching this video, prepare a pen and notebook along with the summary sheet found in session 1. Many solutions that are used in our daily life contain chemicals having important functions. However, how can we find or verify the concentration of a given solution? In fact, this can be determined using a volumetric titration. So the volumetric titration, which is the addition of a determined volume of a solution with known concentration, called the titrant. So the addition of a solution with known concentration, called the titrant, over a solution with unknown concentration, called the analyte. And the aim of this titration is to determine the concentration of the analyte, which is often indicated by a color change. Now let's titrate a solution containing Fe2+ by MnO4- solution in an acidic medium. So to do this, we have two reactants, Fe2+ and MnO4-. The redox couples involved in this reaction, they are Fe3+, Fe2+, MnO4-, Mn2+. We have given the reducing potential of each of these two redox couples. To know the reaction taking place, we place the couples on the electrochemical axis. We have MnO4-, which is the stronger oxidizing agent, it has more oxidizing power, and Fe2+, which is the stronger reducing agent, having more reducing power. Therefore, a reaction will take place between MnO4- and Fe2+, producing Fe3+ and Mn2+. So the balanced equation of this reaction, it will be as follows. In titration, the reaction used should be a complete reaction. To verify that this reaction is complete, we find delta E0, so it is 1.51 minus 0.77, the answer it is 0.74. Then is this reaction complete? As we took before, because this reaction has delta E greater than 0.3, therefore this reaction is a complete reaction and then it can be used in titration setup. From this balanced equation, we can notice that the chemicals that are used in the titration, they are MnO4- solution with purple color, Fe2+ solution with light green color, and H2SO4 solution to provide the acidic medium. Because in the chemical reaction we have H+, so this reaction requires an acidic medium. Here it's given that MnO4- has known concentration and Fe2+ solution it has unknown concentration. The materials used in the titration, they are Erlenmeyer flask, burette, stand with the clamps, magnetic stirrer, magnet bar, and 2 beakers. Now before starting titration, we should rinse the burette with distilled water and then with the titrating solution. Also we should rinse the flask with distilled water. So, to start the titration reaction, we fix the burette on the stand, and then we add the titrant, which is here KMnO4, in the burette to rinse it with the solution. We open the tab of the burette over a beaker in order to rinse the burette with the titrant solution. And then we place the funnel and introduce the titrant, which is KMnO4, in the burette 10, we open the tab until the level of the titrant reaches the 0 mark. Now, for the analyte, we withdraw certain volume of the analyte in the pipette to rinse it well before starting. We place them in a sink. This rinsing is done for the titration process to be accurate. And then we take the required volume from the analyte using a volumetric pipette. We introduce this volume into an Erlenmeyer flask. This titration reaction requires an acidic medium, so we should add H2SO4 that makes the medium acidic. We place, using a cylinder, 20 ml, for example, of the hydrochloric acid solution. We place 20 ml of the solution in the Erlenmeyer flask. And now we are ready for the titration process. We open the tab. While stirring the analyte, we complete adding the titrant over the analyte until we have a change in color. We close the tab and read the equivalence volume from the burette. So, in the procedure, as a summary, we assemble the titration apparatus. We fill the burette by the titrant to 0 mark. We put a determined volume of the analyte using a pipette. In this case, the analyte it is Fe2 plus solution in the Erlenmeyer flask. We start adding the titrant until a rapid change in color occurs in the flask and persists. This is the equivalence point. Stop adding the titrant and record the volume of the titrant added V equivalence. Now, how to read the volume at equivalence point? We know that the graduation of a burette starts from 0, and between two big graduations we have 1 milliliter, and each 1 milliliter is divided into 10 small graduations. Each corresponds to 0.1 milliliter. The volume at equivalence point corresponds to the volume of the solution released from the burette. So, the volume between 0 and the free surface of the solution inside the burette. So, the solution in the burette, which form a concave line or concave surface, we should read the volume that is tangent to this concave surface. So in this case it is 5.2 because it is concave and tangent to 5.2. In this case we can see that the surface is tangent to 6.4. And let's see another case. In this case the tangent is at 17.3. So the equivalence point corresponds to the end of a titration reaction. It is determined by a change of color in the reaction system. If we look at the titration process at the molecular level, as we can see here, we have the analyte, which is Fe2 plus in this case, and MnO4 minus in the burette. Upon adding MnO4 minus over Fe2 plus, a reaction takes place. So, gradually, Fe2 plus and MnO4 minus are reacting and transforming into their products. At this point, we can notice the change in color, and we can notice that all Fe2 plus have reacted, and also the MnO4 minus, they have reacted. So we can say that this point where we have a change in color, it is the point at which the reactants, they are in stoichiometric proportions. So according to the equation, we have at equivalence point, the reactants are in stoichiometry, So the ratio of Fe2 plus is equal to the ratio of MnO4 minus. Therefore, N of Fe2 plus over 5 equal N of MnO4 minus over 1. MnO4 minus is added from burette and Fe2 plus is initially present in the beaker. Now, instead of the number of moles, we can place C times V. So, C times volume of Fe2 plus that was initially added in the Erlenmeyer flask, and here we place concentration of MnO4 minus times the volume equivalence. We know the volume of equivalence point using the burette. We know the concentration of MnO4 minus because it is a titrant. We know the volume of Fe2 plus initially added in the Erlenmeyer flask. Therefore, we can determine the unknown concentration of the analyte, which is in this case Fe2 plus. Now, concerning the colors at equivalence point, MnO4 minus has a purple color. It changes into Mn2 plus, which is colorless. Fe2 plus having light green color, it changes into Fe3 plus, which has a rusty color. So the final solution, it's a mixture of Mn2 plus and Fe3 plus. However, because the solution obtained is diluted, so the color is practically colorless and it turns to pink by the addition of just one drop of MnO4 minus, which corresponds to the equivalence point. The characteristics of titration reaction, as we mentioned before, it should be complete, having delta E0 greater than 0.3 volt. It should be spontaneous, so having delta E0 greater than 0. It should be rapid and unique, so it's the only reaction taking place in the beaker. As an application, we have a 0.2 mole per liter solution of KMnO4. It is added to 10 ml of Fe2 plus solution of unknown concentration. Write the balanced equation of the reaction and finally determine the concentration of Fe2 plus solution. In this application, we can notice from the given that we have two solutions, KMnO4 and Fe2 plus solution. Which one is of unknown concentration? In fact, Fe2 plus it is the one with unknown concentration. Therefore, Fe2 plus it is the analyte, and KMnO4, because it has known concentration, it is the titrant. And as we said before, the titrant is placed in the burette and the analyte in the Erlenmeyer flask. Therefore, MnO4 minus will be placed in the burette and Fe2 plus in the Erlenmeyer flask. What's the balanced equation of the reaction taking place? We have given the couples that are involved in this reaction along with the values of E0. We place them on the electrochemical axis. We notice that MnO4 minus has stronger oxidizing power and Fe2 plus it has stronger reducing power. So they react spontaneously together, producing Fe3 plus and Mn2 plus. After balancing the equation, we get the following reaction. In the second part, it's required to find the concentration of Fe2 plus solution. Given the volume added to oxidize all Fe2 plus, it is 5 ml. So the volume equivalence, it is 5 ml. And the volume of the analyte, it is 10 ml. The concentration of the titrant, it is 0.2 mole per liter. To find the concentration of the analyte, which is Fe2 plus, we start by writing at equivalence point reactants react in stoichiometry. So the ratio of Fe2 plus is equal to the ratio of MnO4 minus. Fe2 plus is initially present in beaker and MnO4 minus it's added from burette. Instead of each number of moles, we place C times V. In the first case, we have C of analyte, solution S times the volume of solution S. In the second case, we have the concentration of MnO4 minus times the volume equivalence. Now, as we can see, we have three terms. They are given in the question. It is the volume of solution as 10 milliliter, the concentration of MnO4 minus 0.2 mol per liter, and the volume equivalence, which is given 5 milliliter. So we can find the concentration of the analyte. It will be equal to 0.5 mol per liter. Thank you for your attention. This PowerPoint is prepared by teacher Ali Bakri, recorded by teacher Zainab Yassin, translated by teacher Mustafa Tles, and supervised by teacher Hiba Badaw.